In this video, I want to talk about inference for simple linear regression. Specifically, we're going to focus on the slope. Now, you might wonder, what about the coefficient of determination? We're going to see inference for that as well, but I'm holding that as well as some other topics in inference until we get into multiple linear regression. The same concepts will apply from multiple linear regression to simple linear regression, but it's a broader context. And so simple linear regression is a special case, as we will see, of multiple linear regression. And for various reasons that will probably become more obvious to you when we do it, I'm holding off on inference for the coefficient of determination until we get to multiple linear regression. So let's just look at the slope right now. I'll also go ahead and show you some R functions for the getting confidence intervals or hypotheses test for both slope and the correlation, but we're gonna hold off on talking in depth about correlation squared until later videos. Okay, so inference for the slope. The prediction model that we constructed from observed data is an estimate of the population model. That is, if you had the entire population of data and you went ahead and constructed a model, that would be the population model. But of course, we never have the whole population of data, so we look at a limited number of observations that are drawn from that population. And the model that we come up with is our best guess of what it would have looked like if we had constructed a model based upon the whole population. Now note, if you still had the whole population, or if you did have the whole population, you would still have error. That is, the explanatory variable doesn't automatically become a perfect predictor of the response variable just because you have the entire population. So don't think of it as though, oh, my estimates are getting better and better and better. No, our estimates of the model are getting better and better, but the model isn't necessarily getting any better. So the population model is what's of interest to us, but we only have the prediction model that we obtained with our sample. The sample slope, what I'm calling here B, what we called B1 earlier in the regression equation we looked at, but I'm just going ahead and simplifying here and calling it B. That estimates the population slope, which we usually use a Greek letter for population parameters, and the same is true here. That's beta. So beta is what we can't actually get our hands on, but we can use B to estimate what beta is going to be. It's our best guess of beta. And as with all inferences about beta depend on a set of conditions. That is what I call conditions necessary for valid inference. Those we will also hold until we talk about multiple linear regression, again, because there are some general concepts that I can exemplify over there that will bear on the simple case of simple linear regression, but go beyond that. And so I'm going to hold those concepts. But keep in mind that in order for this inference to be valid, we have to meet a set of conditions, which we will meet in a later video. A confidence interval that is all positive or all negative suggests that we either have cause or association. The problem is when we have a confidence interval that contains zero. Zero means no association. So if we don't know if the association is positive, negative, or zero, then that's less informative. Although I might suggest to you that if you have a confidence interval that's very narrow, about zero, you actually have provided a good deal of information, namely that you don't have association worth speaking of. It's only trivial. All right, so how do we do this? How do we get that inference? Well, here's our sample model right here. And here I've included the residual. And so therefore I can say that my observed value is equal to my estimate of the intercept, estimate of the slope, slope times the explanatory variable, plus the estimated residual. What we're trying to actually estimate is this population model. The population model has the slope or the intercept for the entire population, the slope for the entire population, and then we come up with the actual residuals. Note that even residuals are estimated in the sample model. So the actual residual, symbolized here with epsilon, a Greek letter, are actually being individually estimated for each participant or each unit of our analysis, individually being estimated with this E here. E is estimating epsilon. So we're focusing on the slope. So B1 estimates beta 1. The slope of our sample estimates the slope of the population. And if we're going to make inferences, we need to know something about the stability of that slope. So here is our standard error of the slope. As a reminder, standard error is an estimate of the standard deviation of a statistic. And you'll note that the standard error of the slope in there is related to how much error we have in our model. Notice the sums of squares error is right here. This sum of squares we haven't talked about before, but that's the sum of squares for the explanatory variable. We're not even going to need to worry about that or interpreting it. We're just going to use it in this formula, but you know what that would be. The sum of squares of the explanatory variable would be if we took the explanatory variable, each value, minus its mean of the explanatory variable, and if we were to square all those deviations from the mean and add them up. So both of those sums of squares are involved in this equation. So the bigger the sums of squares error we have up here in our model, the bigger the sums of squares error, the bigger the standard error is going to be. Conversely, the bigger the sums of squares of the explanatory variable, the smaller the error is going to be. That is, if you have more variation in your explanatory variable, then you actually can hone in on the slope more than if you don't have much variation in the explanatory variable. That should make some intuitive sense from the standpoint that we're looking to see if the explanatory variable is in fact predicting the response, and the more variation we have in that explanatory variable, the easier it's going to be to detect if it does in fact relate to the response variable. Okay, so with a small standard deviation, or small standard error rather, of the slope, we'll be able to have a narrower confidence interval or a higher possibility that we'll be able to reject a null hypothesis. Now we can go ahead and test a hypothesis. Interestingly, if we've met the conditions for valid inference, we use a t-statistic in order to test the hypothesis. And the t-statistic that we're going to use will have n minus 2 degrees of freedom. Oftentimes when people test the hypothesis, they test it against 0. That is, they say that beta equals 0. But you can test it against any value. And in fact, what I would encourage you to do is to test it against all possible values. In other words, build a confidence interval. Because the way that we construct a confidence interval is by testing all possible hypotheses, keeping all those that we do not reject, that is, we retain, makes sense. We reject those we reject, we retain the rest, and everything we retain, we will put in our confidence interval. Another way, a shortcut for getting to the confidence interval is, of course, to add and subtract the margin of error. And the margin of error, as you know from your first statistics course, for the margin of error, you have to have a critical value. Here it's from a t-distribution with n minus 2 degrees of freedom. And you have to have the standard error. Here we have that there. Multiply those together to get the margin of error. So all of this taken together is the margin of error. And then we will have plus and minus that, take the slope plus and minus that in order to get our confidence interval. All right, let's see that actually in action. Let's go ahead and pull up our R. And here in R with our example, down here, I'm going to get confidence intervals for the correlation and the slope with two little functions, one called core test and one called confidence interval, confint. And let's see what they give us. So for the core test, it gave us all this stuff. That is, it gave us the, whoops, sorry about that. It gave us the correlation, which we had calculated before, minus 0.82. But in addition to that, it tested the hypothesis that the correlation was 0. That's the p statistic. I really don't need both the p and the confidence interval. That's a bit redundant. The confidence interval gives me the hypothesis test and then some. But notice that p-value, just for grins, is, notice it's 10 to the minus 13. That is, we're going to move the decimal place over and we're going to have a bunch of zeros in front of that first non-zero value of 3. And so the p-value, for all practical purposes, is about 0, meaning that I can in fact reject the null hypothesis and do so with my confidence level, which I have chosen here to be 95%. That's the default in R. And I know that the confidence interval is not going to contain 0 because the null hypothesis-sized value of 0 was rejected. And so my confidence interval here is all negative values. And in fact, it's a pretty informative interval. It goes from minus 0.71 to minus 0.90. So negative 0.90, negative 0.90 is less than, let me actually go ahead and write it down for us here. So we have negative 0.90 is less than beta 1, the slope, which is less than negative 0.71. So what does that tell me? Well, in the sample, you can see it. You can see it peaking around here. In the sample, we had sorry, I messed that up. We're not doing slope now, we're doing correlation. Let's try that again. So that's the correlation. Okay, this is rho, R-H-O. That's the Greek letter for correlation. So we're doing the correlation now. So pull this back up here. There's rho. We're doing the correlation. So the correlation, I can see here, the correlations in the sample is minus 0.82. In the population, it's somewhere between minus 0.90 and minus 0.71. So not a real tiny interval, but a pretty informative interval. I know that my correlation is going to be at least negative 0.71 or even stronger. So that's a pretty valuable piece of information based upon my sample data, in which I had 49 data points. Now, I should go ahead and call your attention to the fact right here that this is sort of nonsense in this particular context. We'll look at contexts in later videos where it makes more sense. Why is it nonsense? We're looking at the states of the United States. We're not looking at a sample randomly drawn from a population. So I'm showing you the technique, but then I'm saying things that don't make a lot of sense. So if you can translate these nonsensical statements into a more sensical context, which we'll do later on, then you can apply these principles. But we should always remember our context and remember the fact here that talking about things like making inferences to the population doesn't make a lot of sense here. All right, what else did we have? So again, some more nonsensical stuff because we're going to pretend as though we have a random sample from a population. Now we've got the slope to look at. So looking at the slope here, remember that our slope back up here was about -6. -6. Every degree going north in latitude resulted in 6 less mortalities per 10 million people. But in fact, if I had drawn this as a random sample from a larger population, I'd be able to say that it's somewhere between -4.8 and -7.2. So now I can actually write in that beta that I got carried away and wrote in before. So I have -7.2 is less than beta 1 is less than -4.8. Okay, so these would be our confidence intervals if we were talking about 49 data points drawn from a larger population of data points. And by the way, I don't know, since the data was supposed to be the states plus DC, I guess maybe we're only looking at contiguous, the lower 48, the contiguous United States. And without Hawaii and Alaska, I'd have to look. I'm not sure why that data set only has 49 values in it, but there you have it. Okay, so that's all we're going to do right now for inference. If we go back and look here, you might notice something. You might notice that we have some significance codes here that are reflected up here in the ANOVA table, and indeed there is inference going on in the ANOVA table, but that relates to the coefficient of determination inference that I told you. We will do that later on. So I think we've pretty much covered this example and we're ready to move on. I'm going to do one more video in which I talk to you about a few of the things we need to consider when we're looking at bivariate relationships, and then we'll move on to multiple linear regression.